Okay, in this segment, we're going to talk about drug families. Turns out that many drugs occur in little clusters of similar chemicals with similar effects. We notice this, and it's good to be aware of some of the ways in which we group drugs together and why. So when you think about a drug, or even two drugs, you can think about how would I group them together, and there's a couple of obvious ways to do it. One would be the diseases that are used, the diseases for which the drugs are used to treat. Of course, you might want to group drugs together like that. Makes sense. You also might want to do it based on the mechanism of action. Mechanism of action. How does the drug work? What is its target? What are the pathways it affects? If two drugs affect the same target and the same pathways, that would be a reason to group them together. And then, of course, you might want to look at the chemical structure. You might say chemicals that are similar should be grouped together as well. And those are all totally valid ways to group together drugs, and they are very different. This is about where you are in the anatomy and the disease space. This is about how the drug works. This is what the drug looks like. I can assure you that I can come up for any of these. I can come up with drugs that are similar by one measure, but different by other measures. So I can think of many chemical structures that are similar, but don't have the same mechanism of action and are not used in the same disease. I can come up with many drugs that work the same way, generally speaking, but they're used for different diseases and they have very different chemical structures and so on. There is a very useful taxonomy called the ATC taxonomy for drugs. And it is a very sensible, and it stands for anatomical, therapeutic, and chemical. And these actually kind of map to these three ideas. And so the ATC is a well-established way to classify and group together diseases. And I want to give you an example of one such categorization. I'll do this in black. So an example anatomical code might be alimentary. This is the GI system. So that's going to be an A-type code, alimentary. And in fact, in the system, that gets the number 1. And then there's 2 would be, for example, neurological or skin, dermatological. But we're just going to talk about alimentary here. Then you would have a therapeutic class, such as diabetes. So among all the diseases of the GI system, you can consider diabetes also as an example of that, but this is now more in the therapeutic mechanism of action area. And this could be our second level. Then we can go to a more detailed therapeutic level, which might be blood glucose control, blood glucose lowering. That actually is also a mechanism of action, so it's also a T category, but it's more specific than diabetes. This would be the third level. Now you can talk about chemical structures. One class of chemical structures are the biguanides. These all share a similar chemical structure, and that would be our fourth level. And then you get finally, at the bottom of this tree, to a specific drug. We'll take a famous biguanide used in diabetes called metformin, and that would be level 5. And so this is how all drugs have been classified. A drug may have multiple uses, and therefore it may appear in this classification multiple times. And I'll say a little bit about multiple uses in 1 second. So in fact, the drug metformin has a code. Alimentary is actually encoded as A. Diabetes is coded as a 10. Blood glucose is subcategory 3 within that. Biguanides are a subgroup or a subgroup A, and metformin is the second O2. So literally, the code for metformin in the ATC coding system is A10B. Oh, I said. I'm sorry. This is a mistake. I meant to say B. A02. That equals metformin. Now, I said something kind of interesting a few moments ago, which is that sometimes a drug might have two ATC codes, or it could have two ATC codes. And the reason that's sensible is sometimes we use drugs for two different purposes. This is not the case for metformin, but you could imagine a drug that might be used for a GI disease, but also has a use in a hematologic disease. And therefore, you would have hematology, you would have a different disease, you would have a different blood, a different function here. Then you would get to a chemical structure and to a specific drug. You would wind up with a different code. That's okay, because what we now know is that many drugs can be used for many purposes. And let me just say a little bit about drugs and their purposes. Drugs are approved by the FDA with a specific purpose in mind. So a drug company goes to the FDA and says, we think that drug is good for disease X. And the company provides evidence based on the effects of the drug, the pharmacodynamic effects, that it works for disease X. And then if the FDA is compelled by the evidence, the FDA will approve. And what it approves is the use of the drug D for disease X. When the drug hits the market, physicians and other providers are allowed to use that drug not only for disease X, but using their medical judgment, they are allowed to use that drug for other purposes. Those other purposes are called off-label uses. So this would be the labeled use. This is the on-label use. It's approved, and FDA approves it for on-label use. Once it's on the market, healthcare providers are allowed to use it. This is not against the law, are allowed to use it in off-label uses. Why do they allow this? Because when the drug comes out on the market, people start to see its effects on a large scale. And they may realize that although it's good at treating X, it has other effects that are useful for other diseases. And you don't want to stop that. If it's going to help patients and if it's safe, and of course the FDA approves it partially based on its safety, then you want to encourage off-label uses. This has led, so this is very important, and there are many drugs where their use for their off-label uses far outweighs the use for the original approval. Many drugs that we use every day, many physicians can't even tell you what it was approved for, but they know what they use it for every day. This has also led to the idea of repurposing of drugs. And in fact, it enables repurposing. The idea of repurposing is that you take a drug that has certain effects, and you look at its side effects, and you may notice that those side effects, although they're irrelevant to the disease for which it was originally approved, might actually help another disease. So this gets to the point that I really like to make, which is drugs don't really have therapeutics effects and side effects. Drugs just have effects. And in the context of a disease, they may be therapeutic or unwanted. But those same effects in the context of another disease may be very meritorious. So repurposing is now an active area of interest where people look at all the effects of a drug, not just the ones that were approved for which it was approved, and see if there's a mapping to new diseases, like disease Y, where the drug might also help disease Y. And if you find such a use, you can then use it as an off-label use. You need not go back to the FDA. Just to say, you may need to go back to the FDA if you're going to use it in doses that are much above what it was approved for, because there might be some safety issues. But I just wanted to mention that drugs can be used on-label and off-label. And one of the areas of great excitement for off-label uses is to find new diseases where the effects can lead to the repurposed use of a drug for a new indication for which it wasn't originally anticipated.